All right, we're finally coming to the end of section 11.7, and it's a really long section. We're now going to generalize these ideas of motion in both 2 and 3 dimensions. And we're going to say we're no longer going to restrict ourselves specifically to projectile motion. So you're not going to see things like the accelerations due to gravity and stuff like that. We're just going to have general positions, velocities, and accelerations. The fact that it's still general doesn't, however, mean that the relationships between r, v, and a are no longer valid. They are. So in general, if r is your position function, v is your velocity function, and a is your acceleration function, then to go from r to v to a, we take derivatives with respect to time. And to go from a to v to r, we take integrals with respect to time. Right? Same relationships as we had, it's just that we're no longer going to interpret them as projectile motion or forces of gravity or anything like that. Right? So I should be able to give you any one of those 3, and you should be able to find the other 2. And that's our goal here. The last couple of problems that we did in the last video, in both cases started with acceleration. So I won't do another example like that. Instead, I'll do one where we start from position and one where we start from velocity. So in example 4, this is some general position equation, t plus 3, t squared, and 2t cubed. Notice doesn't look anything like projectile motion. Some other force is creating this. Our goal is to find velocity, acceleration, and speed at t equal 1 second. We'll try to sketch these vectors on the graph of the trajectory. So this function has been graphed by Maple right here. All right, so velocity would be r prime, 1, 2t, and 6t squared. And acceleration would be the second derivative, 0, 2, and 12t. Let's go ahead then and evaluate these for t equal 1 second. So the velocity at 1 second would be 1, 2, 6. And let's see, that means that the acceleration at 1 second would be 0, 2, 12. They also asked for speed, which is always the magnitude of our velocity vector. So in this case, the square root of 1 plus 4 plus 36, or the square root of 41. And even though I wasn't asked to find it, if I'm going to sketch these vectors correctly, I'm going to need to know where to position them. So let's go ahead and get r of 1 as well. If I go back to here and plug in 1, 4, 1, 2. All right, so let's see. I'm going to need to start by trying to locate the point where I'm doing all of this, the position 4, 1, 2. And because of the perspective, that might be a little bit tricky. I'm actually going to use the y value, the 1, to kind of key on here. Here's y equals 1. And if I kind of look at my graph when y is 1 coming out here, it looks to me like maybe my point on the graph would be about there. It's difficult to get the proper perspective. The x value should be 4, so this must be coming out quite a ways beyond what we're really even able to see well, just by the way I've got that graph slanted. The velocity vector is 1, 2, 6. So let's see. I would want to go over 2 in the y direction and up 6 in the z direction, as well as coming slightly forward 1. Now that all said, I do know that the velocity or the derivative is always tangent to the curve. So I can help myself out a little bit here by just sketching my vector and showing it to be tangent to my curve. The acceleration vector, 0, 2, 12, is going to come forward not at all. It's just over 2 and up 12 in the YZ direction. And clearly that's going to be steeper than this one. So I'm going to go over the same 2 but up twice as far. So perhaps this would be an example of my acceleration vector. Again, we could graph all of these on Maple, and I will eventually ask you to do that, and we can see them a little bit better. All right, one more example. Suppose that we've got the function v of t is equal to t squared e to the t, and this describes the velocity of a moving object at time t seconds. If r of 0 equals 2, 4, and that describes our initial position, I'd like to find position, velocity, speed, and acceleration at t equal 1 second. So this time I've started with the velocity vector. I can get to acceleration pretty quickly just by taking the derivative of this. So my acceleration vector is going to be 2t e to the t. R would be the integral of velocity. So that one's going to come out to 1/3 t cubed e to the t plus a constant of integration. Now, I do have an initial position, r of 0, that I'm going to use to help me here. But be careful. Remember when we were doing the projectile motion, we could often just assume the constant was 2, 4. But that's because when we plugged 0 in, we always got 0 for our components. That's not the case this time, right? E to the 0 is not 0. So I better actually plug it in so I get it right. We'll plug in r of 0 equals 2, 4. So r is 2, 4 when t is 0. So I get 2, 4 equals 0, 1 plus c. And so 2, 3 is actually going to be my c vector. So if c turned out to be 2, 3, I can write my r vector as 1/3 t cubed plus 2 and e to the t plus 3. All right, now that I've got all of that, it's fairly simple to just go ahead and figure out everything I need at t equal 1. Let's see, we want position, so r of 1 would be 1/3 times 1 cubed plus 2, and e to the first plus 3. We'll just give a decimal approximation to that. This would be 2 1/3, or 2.3 approximately. And e plus 3 is about 5.7. Velocity at time 1? Let's see, velocity was actually the one that was given to us, so 1 squared e to the first would be 1 and approximately 2.7. Just rounding off to 1 decimal place here to keep things simple. Speed, magnitude of velocity, square root of 1 squared. Maybe I should be careful with my rounding. Let's call that e squared so I don't get too much rounding error. Is about 2.9. And it looks like I wasn't given a unit for distance, so I won't put units in my answer, but you know, it'd be feet per second, meters per second, whatever. And finally, acceleration. A of 1 would be 2 times 1, and e to the first, or about 2.7. All right, so again, given any one of the three, position, velocity, or acceleration, you should be able to work around and find the other two. And that's really all we're saying here at the end of this section. Before we completely quit, I would like to go back and talk a little bit about Maple. We've talked before about graphing the space curves. And I just mentioned to you when we did the last example, I wanted to finish the by hand work here first, but when we did the last example, I did mention to you that I kind of tried to sketch some things by hand here. We had our curve, and then we had our velocity and acceleration vectors. And I said that I would show you how to do that on Maple. So I'm going to go ahead and switch over to Maple, and we'll finish up by doing that right now. Actually, I'm going to have to make another video for Maple because I just realized I can't resize my display, and you're only going to be able to see about half of what I type in here. So we'll make one final video just to show you how you can display some of these things in Maple. And again, I think this might help you when you get to this next test, and I'll ask you to be doing some of this stuff in Maple. So we'll stop there and come back for one final Maple video.